I'm too tired to actually get the work done. So I'm like trying to.
Thank you so much for the introduction, Ronit, and thank you for the invite. It's great to be here on the other side of the Charles River. Hopefully you can also see our new building when you drive to work. And if you want to come and visit, you're always welcome. All right, so first off, let me thank the main people behind this work, which is my student Ting and my former visiting student Antonina, and also Jorge. But before going into the details of what I want to present today, let me give you a little bit of a broader view of what my group MPU does. So right now we're working on 4 main topics: feedback optimization, on-dimensional learning, stochastic optimization with a particular twist. We consider decision-dependent distributions, and recently we started a line of work on safe optimization-based control. And as you may imagine, the main objective is to develop foundation theory algorithms that can eventually enable an efficient, safe, and autonomous decision systems for structures. Now, given today I will focus primarily on 2 topics: feedback optimization, and in particular I will try to show how to merge feedback optimization with some elements and some tools from safe control. Now, the main driver the main application that I will cover in this talk is, of course, power systems. But these tools can also be applied to several other infrastructures, including transportation systems, including EVs, intelligent buildings or smart cities. And recently, we also started looking at problems related to data centers and how data center flexibility can help in order to provide services to the power grid at various timescales. So let's dive into the main topic. And the main topic of today will be this concept of feedback optimization. And let me take a step back and go to undergraduate level courses. So when we look at feed-forward optimization of systems, what we have, we're given a system, and then we formulate a given optimization problem based on the model of the system, a cost, capturing performance or safety objectives, and estimates of the exogenous inputs or disturbances of this particular system. So solving this problem involves utilizing a iterative algorithm that I utilize until convergence, and a convergence has spit out a solution that is subsequently fed into the system. On the other hand, feedback control allows me to have real-time implementation of policies that, given a reference point, can drive the controller will drive the output of my system to this particular reference point in spite of fast-acting disturbances or uncertain disturbances. Now, these two tools come together in a traditional decision-making architecture, whereby at a slower time scale, we solve this optimization problem to produce a reference point for our system. And then at a faster time scale, our controller will quickly regulate the output of or the state of our system to this reference point. So inherently, we have a time scale separation between all these tools, right? And in particular, we need to be in a situation where we have enough time to solve this optimization problem to convergence, right? So we have time for computation and sensing. And when we solve this problem here, we look at everything downstream as something infinitely fast. We look at the steady state operation of our system plus the controller. Now, this architecture is becoming impractical or even infeasible in emerging in modern infrastructure, in particular power systems. Why? Because I may have uncertain and faster dynamics, so I need faster adaptation. The computational time may not be consistent with timescales of current system operation. And we may have time-varying performance, and this time here will be key in today's presentation, as well as operational safety objectives. As an example, suppose that we want to coordinate operation for the buildings in the city of Boston, which is approximately 86,000 buildings, in order to minimize the emission or consumption. Now, if you assume that we just have 1, 2, 3, one PV system, one HVAC system, and one HVAC system per building, plus 3 CVs. This means that we need to coordinate in real time basically 500,000 devices, right? At a time scale that matches the dynamics of prevailing ambient condition or pressure conditions. Plus, we need to sense all the states of the devices, plus also we need to collect measurement of voltages to assess the state of the grid, right? So this is something we cannot do in real time, right? Especially given that at the distribution level, the powers from non-controllable assets may vary very quickly at the order of seconds. So that means that we need to solve this problem here for 500,000 devices at the sub-second level. So this is where the idea comes into the picture, which is to convert optimization algorithms into feedback controllers. And precisely what we do, we formulate.
Question.
Yes.
In your abstraction here, the main challenge is tractability only. Is that the only challenge in the diagram that we had in the previous slide?
Thank you so much. Excellent question. So the one challenge is computational tractability, but the second challenge, which will be emphasized especially in the context of power systems, is the fact that we may not be able to observe or collect information regarding the exogenous inputs W. In the context of power system, this W can be a high-dimensional vector that collects all the active and reactive powers from non-controllable systems. And we like to try to regulate and control our system without having access to this vector here.
But you have in your optimization W in there also.
Yes. In fact, we're going to be moving away and we're going to move it to something where W doesn't play any role. Okay. So this is going to be only a dynamic optimization method that we states only the U, the control input, and measurement of the state or the output of the system. And I'm not going to rely on information about the W.
Just one more clarification
Yes.
question. So you go now to dynamics because you have dynamics of control rather than just discrete optimization. What happens with the natural dynamics of equipment? Are you still doing just discrete time and assuming that that one is stable or whatever?
Yeah, that's an excellent question, which I'm going to touch upon soon.
Okay.
We're going to be, you will see that we're going to have a sufficient time scale separation between the natural
So there
dynamics.
is that assumption has to
Exactly.
be made.
We're going to do.
Okay.
It's actually the main result of the
Okay.
first part. Yes, so for the control synthesis, what we do first is to formulate an equilibrium selection problem where we formalize an optimization problem, in this case where the W comes into the picture, but this is a model for now, where we assume a cost associated with the input, a cost associated with the output or the state of the system, subject to the steady state input-output map of our system, and subject to additional, perhaps, constraints on our state or output. So this problem here effectively defines an optimal operational point that I would like to have for my system, had I have the ability to solve this problem to convergence, and had I had the opportunity to observe my W. What instead we would like to do is to develop, design this block here, so that we're able to drive the state or the output of my system to this particular equilibrium point, again, without having access to W. This is in the static case. If we have a time varying formulation, because W changes or the cost changing, what we like to do, we would like to continuously track this optimal point implicitly defined by this time varying formulation problem. Okay? So this is basically an equilibrium tracking problem.
But I think if you talk about renewables and all these different fluctuations, this is very biased opinion, but there is no notion of equilibrium anymore. You know, things are fluctuating all the time. So can you, in just this sort of at a high level, explain what times are you trying to capture? So you have these fluctuations with renewables, and they change all the
I will
time.
come to the renewable.
But,
the renewable part.
so what is this formulation for? What is T?
So here, so this time,
Continuous time.
continuous time.
We don't do optimization in continuous time. We do it in feed forward. So I would get lost right at the beginning.
Okay. Sorry about that. So let me go back a little bit. So what you're referring to is a setup like this one where
Yes,
we do feed forward optimization, right?
Yes.
You are right. We cannot do it in continuous time.
Yeah.
Right. So what I want to do is to strip out these two blocks and develop a new block that can operate where the math can be computed in real
Continuous time,
time,
okay.
in continuous time, ideally, or in a sample data fashion, whereby I'm able to solve this problem here in real time.
Okay.
And solve this problem here precisely means going after this particular solution that I U star, Y star. And in case of time vary, meaning that we have a cost that continuously changes over time, or a set that continuously changes over time, I'm able to track it.
So it's fair to say this is really a regulation problem
Yes.
now. It's not
Yes.
just equilibrium.
I call it equilibrium selection problem because one of the main results is that the equilibrium point of the closed loop system I'm going to show you coincides with an optimal solution of this problem here. So this is why I call it equilibrium
Okay,
selection.
okay.
We can
Clear
think
now.
about it
Yeah.
as a regulation problem. All right, so just to give you a little, I'm not going to touch about the topics related to learning in this presentation, but just to give you a little bit of a broader view of what my group has been doing. We also ask ourselves the question: can we have access to, for example, the parameters of our system, right? Or can we actually observe the state or the output of the system? Or can we know the cost function a priori, right? And this touches upon problems related to the case where we need to perform instead state estimation, or we estimate the topology of the system, especially for system applications, or perhaps we need to learn the cost from observations, right? So long story short, what my group has been doing was also to look at extended versions where we start adding also learning and perception modules into the closed loop system. And in this particular case, the main objectives, as I will show you, is to claim stability and convergence to these equilibria implicitly defined by these problems, even in case where I'm sensing or estimating the output of the state, or I'm trying to estimate the cost function of the problem. So this gives you, as an idea, this gives you many different kind of combinations for setups that we consider, especially depending on how you model the system, whether it is an algebraic map, or a discrete time dynamical system, or a continuous time dynamical system, the class of problem that you are considering, convex, non-convex, static, time varying, the particular class of optimization algorithms that you are considering, discrete time, continuous time, as well as the particular learning component you put in. So you can explore all different combinations, but for today's talk, I'm going to be focusing on one particular subclass where the emphasis is on nonlinear constraints added to our target optimization problem. And what I want to show you is how to develop this controller, effective feedback controller, by blending notions of gradient flows, control barrier functions, along with concept of online optimization. The first part of the talk, we're going to be considering systems with some given nonlinear dynamics. And this is going to be a generic framework for nonlinear systems, perhaps applicable to different applications. The second part, instead, I'm going to be considering the case where the system can be modeled as an algebraic map. And I will use power distribution systems as a guiding and driving example for this second part. So the first one is going to be a bit up in the air generic. The second, I'm going to use voltage regulation for distribution system as a driving example. Okay. All right. So I'm gonna dive into the first part. But before diving in the first part, I just want to have one slide to summarize what the control barrier function is, since I'm going to be using some elements and tools from that particular chunk of literature. So just very, very quickly, what we have in the traditional CBF literature, we have a control-affine system. We solve the appropriate assumption for uniqueness of solutions and so forth. And we are given a nominal controller, U equal Kx, that perhaps has some desirable properties, like ensure stability of a given equilibrium point. And we also consider a safe set, which is described as a super level set of a given function that is assumed to be continuously differentiable. And as an additional assumption, we also assume that the gradient of this function is different than zero at any point of the boundary of the set. This is just to go back to the pioneering work on Nagumo in the 40s that outline a series of assumptions that eventually allow this set to be forward and bound. Now, there are many papers in this context. I didn't cite all of them, but the definition of CBS is as follows. We can say that this function here, Xi, is a CBF of the set for this particular system if we can find an extended class K infinity function alpha such that for every state that exists a given U, so that this particular inequality here holds. This is nothing but this should be Xi, the Xi dot. So that means that I'm able to steer the dynamics of my system inside the safe set, and I can make the safe set Further invariant.
Can I ask a very quick technical
Yes.
question? Do you consider the safe set to, do you assume that the safe set is bounded?
So we don't require the safe set to be bounded. The further invariant of the safe set is guaranteed, even if the set is unbounded. However, going back to our previous conversation, boundedness will be critical when we study undesirable behaviors that are emerging from this particular safety filter that I'm describing now, where undesirable behavior are in terms of emergence of unbounded trajectories, linear cycles, and spurious equilibrium.
Because, sorry, just one
Yes.
short comment and then I'll stop. So the moment you start to sort of look at the combined space of stability and safety, and you say, okay, just in terms of conceptual property of safety, you want to be in this
Yes.
space and it doesn't make sense if it's unbounded, then immediately any kind of assumptions that the safe set is bounded sort of negates any kind of global stability
True.
need at all.
That's correct.
So you've already assumed that everything is
Absolutely.
bounded. So I was just curious how you did.
Absolutely, absolutely.
Thank you.
Absolutely. When I'm not going to touch this issue in this talk, but when I talk about stability of CBF, I mean, we have an infinity function so that we can have some given, especially with dynamics. Anyways, just as a very last note, what people have explored in the literature was to design these safety filters, V of X, whereby we are trying to minimally modify the action of the nominal controller in order to guarantee that this condition here is satisfied, right? So again, the objective of this modified controller or safety filter is to ensure that we stay inside the set S, okay? And this is something that we are going to use in our framework in conjunction with non-line optimization to tackle constraint optimization problems.
What is
Yes.
Yeah, exactly the same question.
Kappa is a nominal controller that has already been designed and is given to you. It has some particular desirable properties. For example, it stabilizes an equilibrium point, but however, it's not guaranteed to ensure safety.
In this particular viewpoint, there is no other cost function in addition to safety specification, right?
Correct.
Sorry, when you said like you can steer to safe set, does that mean that you have some controllability assumption? Or?
Correct. That's another assumption.
Sorry, so you could have a cost function implicitly
Yeah.
because you might be asking for some performance.
Yes.
In which case, in addition to the stability safety friction, there could be a performance safety friction as well.
Can you explain in English what is that inequality?
Yes, so basically this, sorry,
No, the second, that inequality.
so this one is basically, sorry, I mixed up the symbols. So this is supposed
The
to be
notation
Xi.
error.
Yeah,
This is nothing but the lead derivative of my function Xi along the dynamics of the system. And this is nothing but an extended class K infinity function applied to h of x, the Xi of x. So it basically tells you that you are trying to steer the dynamics of your system to a direction that you enter the safety set if you're starting outside, and if you are already inside, you stay there.
okay, thank you.
Sorry for the mix-up of the symbols. All right, now I'm ready to go into the first part. So what I'm going to be considering is for this first part is this generic setup where again I have some nonlinear dynamics, and this is my feedback optimization controller that I would like to design. And I'm going to start outlining some standard assumption on this nonlinear plan. So I'm going to be assuming that this f is continuously differentiable and ellipsis continuous in its arguments over a given domain that is appropriately defined. And then the one assumption is that for any fixed set of inputs, u and w, there exists a map H so that this equality here holds, right? So H of u and w is the unique equilibrium of the system for given inputs u and w. This is just to make the problem well posed, but an additional assumption is that this particular equilibrium point is also locally exponentially stable. Why am I making this? I'm not going to go into the details, but I'm making all these assumptions because I can leverage converse Lyapunov theorems in order to estimate the given region under which I have a well-defined Lyapunov functions associated with this particular dynamical system. Okay. So this is just a standard set of assumptions that allow us to set up a well-posed regulation problem. Now, going to this particular block here, what I want to do is to again formalize this target optimization problem that I would like to ideally solve had I has access to W and I had access to infinite computational resources. Now, in this problem here, we're considering costs associated with the inputs. And in this case, I'm going to be considering costs associated with the state of the system. And now the key novelty of this particular work is that I'm also be considering constraints associated with the steady state of the system, okay? In addition to constraints on the input. Why? Before doing that, let me just tell you why the majority of the works in the context of favorite optimization deal with unconstrained problems. So adding constraint to the system is one of the major contributions of this particular work. I'm just going to try to provide here a minimal set of assumptions that may look a bit involved, but they are minimal in the sense that they allow me to consider classes of non-convex optimization problems while still offering strong stability results of my interconnected systems, as I will show you in a few slides. All these assumptions can be relaxed if I want to formulate a convex optimization problem, and I will have a global stability result. But in this case, I want to stick to this minimal set of assumptions. And the first one is that I'm defining the set UC of inputs, of feasible inputs, and I'm assuming that this vector valued function gamma that defines the constraint of the inputs, of course, is the gradient is non-zero in any points of the boundary. And I'm also assuming that these functions gamma have a locally ellipsis continuous gradient or Jacobian. I'm also going to be assuming that although non-convex, this problem here may have some KKT points that are local minimizers and are isolated. And I'm going to be assuming that when I look at these particular KKT points, the LICQ condition holds at these particular points. And on top of that, the functions that specify the cost and constraints are twice continually differentiable, and the Hessians are also positive definite at that point. Yes.
So in a way, what you want is zero duality gap.
This is where I'm going. That is precise. So what I want to have is to find a minimal set of conditions such that if I'm working around in a neighborhood or in a region centered on these points, I'm going to have strong exponential stability guarantees. Again, if we consider a convex problem, all this goes away and we can have global conditions.
So I'm a bit confused in just conceptually. The feedback optimization, the U is the controller is a function, right? You have to design here is a finite dimensional.
I'm designing the G, the map.
But
Okay.
it's numerical, right? It's not explicit. Is it explicit? That's
I will
think,
show
the
you.
question.
I will show you. This is the map.
Okay.
So if we take out all the constraints, you just consider this function here, you can use a simple gradient map. Simple, however, you see that here I'm replacing the X instead of the steady state map, right? So does this address your question? So in this case, I'm considering a specific class of maps that are defined by the gradient flows. However, and we have results when we look at this interconnection. However, let's put back the constraint. And what we do now is to design something that brings together a gradient flow with the CBF. Now, first off, open loop setup. So let's forget a little bit about the dynamics for now. The way I'm designing the G in this particular case is to take the gradient of the cost function. And then what I'm going to do, I'm going to replicate the equations of the CBF filter. And I'm going to replicate this equation for the CBF filters for every constraint that I have. So for these constraints on the output, on the state of the system, and for these constraints on the, where again, this one is nothing but the Lie derivative of my dynamics with respect to the CBF defined by the constraint function. However, I want to point out something. If you see here, I have the steady state map, right? Age of UW. So what I'm going to do now, merging also the concept of online optimization, I remove the map with measurements, thus creating this interconnection. Okay. So I get the measurement of the state, and then I replace it inside the gradient flow, and I replace it also here in the computation of these Lie derivatives. Okay. So overall, I come up with this interconnection whereby I have an interconnection between this dynamic plant and then this controller with the map G implicitly defined as a solution of this QP. This is a QP for any given X. Now, let me make another assumption. And what I'm going to assume is that for every X in a given region of interest, this QP here is feasible. And I'm also going to assume something else, that the Mangasarian form with constant qualification and the constant condition hold. Why am I doing that? Because I need to make sure this map G is locally Lipschitz in X and in U, so that I can guarantee existence uniqueness of solutions. So this is just a technical assumption for me to have uniqueness and existing uniqueness of solution for the interconnected system.
What is eta?
Eta is just a controller gain that multiplies the map G and will play a role now in assessing the stability of the interconnection.
So I hear this. I've always had this problem. You remember Alec Kapcic did that? I mean, didn't make his tenure at Harvard because of this question. You remember Alec Kapcic what?
Sure.
Well, he always replaces the equation, the output with the measurement.
Yes.
And from there on, life is easy. Is there anything hidden in doing that?
So first off, I'm glad I already have 10, you know.
I mean, it really was a killer question, and now you
So
just
so here is a, so let me take a step back. So if I
So can you explain the question? I think it's.
oh, sorry. Yeah, maybe you
so
want to.
I don't have tenure, that's why I'm sorry.
Oh, guys.
basically the trick here is just to replace this algebraic expression here, h of UW, with measurement of the system, right?
So essentially you remove W and you remove.
Yes. But
We
this is
just get the
precisely
information through measurements, and we used to do that with state estimation long ago with observers. And I think this is a sort of really weird question about when we want to do machine learning and control. You know, you always say, okay, I don't know these mappings, I don't know these models, and I'm going to just replace them with some measurements, and I'll estimate what it is. So I think this is a very hidden trick, I think. So,
yeah, yes.
but what does
But-
it,
But
is there anything that may
So-
go wrong?
so no, I will show you that hopefully nothing goes wrong.
Okay.
Otherwise, but the main takeaway is the following, right? So here, if I want to run this algorithm, that this will be open loop in that particular case, right? There is no interconnection with the system, right? I need to know the W. Here, I don't want to measure the W. In a constant power system, W is again the powers consumed or generated by non-controllable assets. I don't want to monitor them. So what I'm going to do, by replacing the H with Q and W, I can get away with the need of measuring W. This is just the main benefit of this trick.
I mean, Maria, if you were to take your question and really look at it at a meta level, that's
Right.
sort of the entire basis of control. So control systems basically say a feedback control. So control systems are predicated on measurements providing insight into how a system is behaving,
Okay.
as opposed to knowing a model that predicts as to what that system variable would be. And what Emiliano is doing is to leverage that, hey, once in a while you can measure, in which case it alleviates the need for having an accurate model.
But there
Which
has to be
has-
some validation, come on. There has to be some validation that these measurements reflect the actual model and
Which is
stuff.
what people are, yeah, there is a whole bunch of literature that
Right.
says feedback optimization works under certain conditions, and that's basically what this is.
Under
what
condition
do
that
the-
measurement
But
replaces.
I'm just measuring it.
Sure.
Yeah.
Yeah,
So what I can tell you is that I'm not going to show it in this slide.
we'll do it
But-
later, okay.
No, we can
We'll
do it on
talk
the board
later.
later, but what I wanted to show you is that if you assume for a moment that your measurements are error-free,
Well,
You can-
that's a huge.
no, wait.
Okay,
If you assume for a moment that the measurements are error-free, you get, as we show in this slide, local exponential stability guarantees. If you assume that your measurements are affected by errors, and if you make the assumption that the error is bounded, we can get practical local exponential guarantees, meaning that you converge within a ball centered around the equilibrium point, right? So I'm going to show you this one. Before, let me just state one intermediate result. So we are looking at this interconnected system, right? Again, this dynamics with the controller that I showed with this particular coefficient eta. It's just a game for now, right? And I have this problem. So first of all, I'm creating this connection between equilibrium points of this closed loop system and KKT points of this interaction problem. And this is precisely in this proposition, right? So we say that in equilibrium, that there exists a pair, there exists a lambda star, so that U star lambda star is a KKT point of this problem, if and only if this one is an equilibrium point of the closed loop system. So this is the first intermediate result. The second result is that this closed loop system renders the set of inputs polar invariant. So I have all the appropriate constraints on the input satisfied. Now going to this.
Can you provide an intuition for the proposition
Yeah.
with regard to how exactly should we understand this?
So
connection?
this is by construction
Yeah,
because
the first one, yeah.
so the first one is just basically writing down the KKT equations associated with this problem, writing down the equations, the equation for the equilibrium point of this problem. You see there is a one-to-one match by design, done by design.
I mean, the first one is zero duality gap, essentially.
This is just to provide a result that if this closed system here converges to a point, the point is not something random, but it's precisely a KKT point of this problem, which is what I wanted to have. And when this is convex, it's basically one global minimizer. Now, the main result, okay, suppose for a moment that we have perfect measurements. Suppose for a moment. Now, the result is as follows. Here we have the interconnection of two subsystems that when taken independently, they are stable. But when we stitch them together, they may not be longer stable, right? So the result is as follows. We can play around with this eta, and let me just gray out things that are not necessary for now. The result is as follows. There exists an eta star, which I can write down in a mathematical rigorous way, and I'm not providing the expression here, so that if I pick the eta, the gain here, less than this eta star, I have these results in terms of transient, right? So the distance of my x and u, the extended state of the system, on this equilibrium point, decreases exponentially as time goes by. If I start in a starting point, xt naught ut naught, that satisfies some particular assumption that we cannot, I'm not going to cover now. But this is a practice, a local exponential stability result for these interconnected system. Now going to I'm going to skip this 1 second, I'll go back, but I want to go to this particular result. If now we assume that we have errors in the measurement, x, or if we further assume that we implement G approximately, for example, have an early termination of the QP solver, I can still derive this practical local exponential stability result, where I just add these particular terms, and E, capital E, is a bound of the maximum error that I commit in the measurements, for example, and kappa is just a constant that I can derive based on the particular mathematical properties of the system and of my controller. And by mathematical property, this is very much related to the Lipschitz constants of my system controller. Yes.
Is this then bounding the time in which you need to compute your optimization?
So so in this particular case, I'm assuming that this optimization, this QP can be solved sufficiently fast. We also have an additional results in terms of sample data implementation, where we do have an upper bound on the execution time that so that stability is preserved. But in that case, we have we still have local exponential stability, but basically it tells you you need to execute it sufficiently fast. What changes is just a term here, this law, and then an additional the A is different, but the result is better. Yes.
So you make, this is a very nice result. You make this interesting point about this eta star and the properties of this composed dynamical systems.
Yes.
But with regard to the actual properties of individual dynamics and the things that the composition should satisfy, what are the kind of key necessary assumptions on the two subsystems?
Yes, perfect.
For the things to actually work and when this may break?
Yes, so the two necessary assumptions is that the two subsystems, when taken independently, are stable. Yes. Meaning that I take the data plan, I fix the U and W, and it's going to be locally exponentially stable. And the same applies to my controller. But again, the key here is that, as Kokoto was explained in the 60s, when we stitch them together, you need to have this sufficient timescale separation. And this eta is basically precisely telling you that they can be stitched together, but there needs to be, the controller in this case needs to be sufficiently slow in order to preserve the stability of the closed loop system.
It's like composite control, right? Under separation.
Yes.
Yeah, okay. Yeah, that's maybe a good way to think about it. Is, you know, like composite control comes from optimization and the other one comes from regulation stabilization. Is that the generalization?
Yes, this is the general idea.
Okay.
So we want to merge them. But as you said, this basically tells you that you can compress time scales, but not too much.
Is there a negative result?
You mean?
Is there a negative result?
Negative.
Yeah,
there are a
which
lot
sense?
of them.
In which sense?
In the sense of actually when things would break. So assume that individual systems
So
are.
by the way, this is, okay.
It's a fair question.
It is a fair question. So I can tell you that these bounds here are very conservative. So I can guarantee you, at least for all the gazillion simulations that we run, we can push this eta very close to eta star for many cases. Of course, they can be, this is a positive result, right? Because that means that if you exceed n star, things can go wrong, meaning that you lose stability, right? So I would actually see it as a positive result, as opposed to stitching things together and close the fingers. Right? Does that make sense?
Yes, actually, you know, this is not for online discussion, but I am struggling with what does it mean for some skills. I would love to follow up because, you know, this measurement, this is what bothers me, that measurement.
Yeah. Right.
That measurement is right now what we have, as systems are changing. You have to model the X sufficiently fast dynamics so that it's not the error. Like in power electronics, we have power electronically switched stuff. So that is a fast dynamics that you can either interpret as an error, in your measurement if you didn't model
Yes,
it,
right.
and I think there is now army of people working
Yes.
on that stuff, which if you model it, you are in big trouble because it's too complicated.
You're right.
So can you replace it with measurement? That's why I was reacting.
You're right. You're right. This is, you're bringing up an excellent point, especially when we talk about power electronics. So we can talk, but the bottom line is that you will still need to have a physical separation between the switching and the electronics level and this sort of event, right? Because you need to make some underlying assumption on the.
Yeah.
But anyway, this was just before.
Is there, just
Yes.
one very quick technical question. Is there, can you do local equilibrium by local, or you have to have unique equilibrium in the area that you are claiming the results? Is it just
This is just a local result.
local exam for nonlinear systems, you have multiple things? So this is one by one?
Yes, correct. But if you, for example, I skip this slide, but if you consider an LTI system and then you consider a case where the associated attenuation problem is convex, then this is actually global. Okay.
Very interesting, yeah.
Well, I prepared just like this slide, but I will probably just keep it. Just to show you that this can be applied to power systems, perhaps we can start offline. But I'm gonna try. I just have probably 10 minutes, so I'm gonna try to delve very quickly into the case of static plants. And as I promised, I will use the voltage regulation problem as a guiding example. So in this particular case, we have that the system doesn't have prevailing dynamics, so the dynamics are sufficiently fast so that I can just consider the input output steady state map. And this map is gonna be capital H. And I'm going to be considering a distribution feeder. So anything downstream is substation, right? And I'm going to be assuming that the distribution feeder has a number of distributed energy sources, controllable. And what I'm going to be controlling, my U, is precisely the active and reactive powers of my DRs, okay? The W, as an example I was trying to make, is going to be basically the active and reactive powers of all the other non-controllable assets in the system, which I don't want to monitor. And then the X, in this particular example, can simply be a vector collecting the voltage magnitudes at some points that I want to monitor. And accordingly, the ith component of this vector value function I is just going to be a function that maps powers into voltages, which exists based on implicit function theorems. And there are many people also from ETH, right, that shows this existence.
So there was an S there, which was, I forgot, what is S? You did not explain.
Oh, this one?
Yes.
So this is the complex power. So what I'm going to do here is just stacking in the U, the active and reactive powers, right? Now, based on this, the problem that I'm formulating is going to be an instance of the so-called AC optimal power flow, where I'm trying to minimize the cost associated with the active and reactive powers of the DRs and the cost associated with the voltage magnitudes. But then I'm going to be considering constraints on the operating region of my inverters, right? So this is the classical requirement. I think this is in Europe. And then I'm going to be considering constraints on the voltage magnitudes, right? According to the well-known standards, right? So again, for example, this can be 0.95 pu, 1.05 pu. So this is my target problem. And again, if you solve an OPF, you need to know the W, right? Now, by using this closed loop that I'm proposing, I'm going to be solving this online based on voltage measurements and without measuring the powers from the non-controllable assets.
Just a side comment, I think it's much easier to measure power accurately than voltage, just as a side comment.
Yes, and then we can do.
That's why I'm so sensitive to this accuracy of measurements.
Sure. Yeah, that's true. But then we can solve the powerful equations and find the voltage. Right?
The accuracy of voltage measurements now in both power systems, you will be shocked, 2%.
Really?
Yes, it's horrible. You can't do even, I don't know if you know, optimization. So you measure accuracy of voltage magnitudes within 2% of it. And you're optimizing within 2%. So what are you doing? So the measurements have to improve, I think. Anyway.
Good feedback for Eversource and
I'm sorry.
Anyways, as a small side comment, given some of the programs that are here in Massachusetts, you can also include perhaps constraints on this particular form, with P0 is the overall power flowing in a substation, right? And perhaps you want to track it even a set point, but I'm not going to be considering this in the next few slides.
Just a quick question, Emiliano.
Yes,
Like,
sir.
the satisfaction of the like nodal power balance, like where is that in here? Just like where should I think of it in this notation?
Yeah, this is implicitly defined in this map here, right?
Okay.
Because I'm assuming that the dynamics here of the power electronics are sufficiently fast so that I can consider powers and voltages in the phasorial domain. Because again, I'm looking at anything downstream the substation, right?
Mhm.
And I'm assuming the implicitly that the feeder is stiff.
Is the linear map or not?
No, this is not linear.
H is not linear.
It's not linear.
What kind of,
Well, it comes from the AC power flow equation, so basically quadratic. But fortunately satisfies all the assumptions that I made in the previous part of the talk. But anyways, so this one, right? This one becomes my safe set, right? So I want the voltages to be within limits and all the powers inside my operating region of the inverters. So now what I'm gonna do, let me skip this part here. I'm just gonna create this closed loop system, right? Where again, my G here is given by the gradient of the cost of the OPF. And then the constraint on the voltages and on the powers are dealt with by taking again this CBF type approach. Okay? That makes sense? But so in this case, you see that this G here, which is again the Saltian solution map of the QP, tries to minimally modify the gradient or the negative of the gradient, while ensuring satisfaction of the constraints. Sorry if I'm going fast, but I'm running out of time.
so the safety specification is this constraints in the original flow?
Yes. Correct. Now going to the comment on the function age. Here you see that unfortunately to compute this, right? The gradient of age. It's very hard to compute the gradient of the Jacobian and power equations. So what we actually do in the implementation is to leverage an approximate model, right? Which is approximately linear in the controllable powers and in the W. And then based also Marisa's feedback, we can also leverage pseudo measurements if we are not able to have access directly to measurement of voltages. However, practically, all these errors that we introduce in the computation of the Jacobian and in building the pseudo measurements are bounded. And here is just a plot just to show you that for some standardized systems, so this is for a particular European system, the error in Jacobian is actually bounded and very small. So what we have in this case, we have this closed loop system where our method computes the power set points of the DRs based on measurements of the voltages. We send down the new set points, and then we collect pseudo measurements. We leverage our linearized model, and we keep going in closed loop. We continuously perform these steps in closed loop. Now, informally, we can show that this closed loop system renders a KKT point of the optimal power flow problem that I formulated, again, practically locally asymptotically stable, where again I have this forgetting factor here, that's typical in the exponential stability. And then we have this constant term here, where now I have two terms, EJ and EM. EJ is the bound of the approximation error of the Jacobian, and EM is a bound of the error in the measurements. So this is a practical local exponential stability result. Now, most importantly, we have a practical forward invariance of my set of voltages in the system. This basically tells you that the set S, which remember again, collect upper and lower bounds on the voltage and the feasible set of my inverters, So in inflation, where the radius of the ball is proportional by a small factor to EJM is Fourier invariant. Okay. And again, if magically these errors here are not present, the actual region is Fourier.
Why does it have to be an isolated KKT point?
Because the ACOPF is non-convex. So you can have several KKT points, but isolated because here is where the cheating part comes into the picture. Isolated because I'm looking at the curvature of the cost function around this isolated KKT point, and the curvature has to be such that at least quadratic, so I can derive these local exponential stability results. If it is not quadratic, I can just get away with asymptotic stability, practical asymptotic stability.
I was trying to imagine like how would you implement things computationally, and then like you have the you need to solve powerful equation to
Oh no, we don't
You
solve
measure.
equations. You use measurements.
the measurement.
That's the whole
I
trick.
see, I see. And then previous problem formulation, you have H expression. Then that's not.
The H comes, we are leveraging, sorry, I went fast, but we're leveraging this approximate model, linear model, and you can compute the matrices R and D offline based on the topology of the system and the data that the system provides. Perhaps, let me just show one quick simulation result and then I'm over. This is a test system available, multi-phase. We load up this system with PV generation, and the trajectory was taken from this open power system data. Again, the inverters are operating according to this standard. And the cost that we added in the OPF was the cost of curtailing renewable and the cost associated with the amount of active power that we use. So if we do nothing, meaning that we don't even implement Volvar, we have during the course of the day a trajectory like this one for the maximum voltage, absolute voltage over the network. And these blue lines represent the number of nodes that are impacted by these overvoltage conditions, right? But what is happening here is that if you have overvoltage condition for more than a few seconds, the inverter will shut off to protect itself, right? So what we implemented here is the following, right? If after 5 seconds there is still overvoltage condition, the inverter shuts off, and then you start a timer and you try to turn back on after a given deadline, right? So this is what we get in that case. This is when you implement the celebrated Volvar control, right? With this particular curve, right? Based on the standard. Now, here I'm looking at 2 methods. First, an online method where instead of using my CBF type arguments, I use primal dual. And I get something that, violates as expected from the theory. But this is what we get using our safe gradient flow approach. So you're able to completely cut the voltages at 1.05 in spite of some errors. So although we have a local practical exponential stability from the theory, in practice from simulations, you completely cut the voltage magnitude at 1.05. So this is good news. This graph here tells you the maximum over voltage duration for these various methods. So without control, Volvar, primal dual, and our approach. And then you see that basically I'm looking at the max, the mean for 1.05, 1.06. But you see that in every case, in our that is the color coded in black is basically negligible, and of course the no control is the most severe, right? Where you don't even implement Volvar control. Lastly, in terms of performance, in terms of cost, here the benchmark is the DO, which means batch optimization, which is the ideal case where I solve the COPF to convergence, having access to infinite computational time, computational power, and having access to the W. And you see that our method basically matches very closely the performance of the batch, which this was actually quite remarkable. after we run the simulations. And here, to respond to one of the questions before, we computed one step of our algorithm every 10 seconds. Okay. Anyway, so the bottom line is that this provides a way for us to implement this. Yes.
Can I ask about your definition of costs there? Why is there a cost of curtailing renewables? Isn't that free, basically?
Or, well, this is what we associated the cost to the amount of power that you curtail, because this is what you can't use in principle, right? So it's like the penalization that we get for not providing all the power that we could provide.
Right, okay. But that power is free, though. It's, it's.
No, that is true. But if I can go back one slide,
It's the opportunity cost.
If I go back one slide, right? So if you look at vol-var control, right? Vol-var, you don't touch the P, you just control the Q. You see that you cannot do much during these times, right? So this tells you that you need to do something else, and this something else is also start touching the P, meaning curtailing. So this is basically inevitable if you want to achieve a voltage profile that doesn't exceed the 1.05. This makes sense?
Sure.
So the method, maybe I'm understanding something wrong, is very similar to primal dual, and you compare it against primal
Yes.
dual. Why is it that primal dual isn't able to, in particular, satisfy the constraint?
Because the primal dual, you also have the dynamics of the dual variables. And when you have so first of all, you have the dynamics of the variable, right? Here we don't have dual variables. But secondly, primal dual method is not guaranteed to enforce feasibility pointwise in time, right? Or iteration wise. You always may have a violation of the constraint, right? Feasibility is guaranteed only asymptotically. Whereas this method here ensures practical further invariance at any time. Makes sense? Right, I'm sorry, I reached the end, but I just wanted to show you a bit,
If you go to the graph at the end,
yes.
yeah, what intrigued me is like you do batch, comparison, and that gives you some numbers, right? If you were to somehow extrapolate those numbers with your U function, is there any similarity between the two, the one that you did by thinking about that feedback optimization?
Use the U function. Let me think.
You're doing the control.
Yes,
right?
yes.
If you look at, you have an explicit formulate, you have explicit function.
Yes.
When you do batch optimization, you just get numbers.
Yes.
Can you extrapolate with the same thing or not?
Oh, no. They are okay.
They are not very similar. No?
Well, they are. I mean,
They become similar.
They become similar. Yes. I mean, this is in aggregate, right? This is the cumulative, right? So I can show the.
Can we have the conversation after lunch?
Yes. After lunch. Yes.
Yeah.
Okay. Sorry, let me wrap up. So I wanted to show you a bit the general areas of my group. Talk to you about this online feedback optimization for constraint problems and applications in power system. I'm happy to discuss further with all of you. And thank you again for the input.
Any question from the online audience?
Sorry.
Okay. Thank you, everybody.
I want to know if Miriam is online. We have a visitor from EPFL who is actually